Hello everyone, my name is Yash Yadav and my enrollment number is DE240228 and I am a student of International Institute of Professional Studies. The subject is Numerical Analysis and Design and this is my second internal test video presentation. So question 1 says the population of a city recorded in a census taken once every 10 years is given. We need to estimate the population in the year 1925, 1975 and 1984. Now, why this is a problem? Because the census was only taken in 1921, 1931, 1941 and so on. Every 10 years exactly, the year 1925, 1975 and 1984 were not directly measured. So we need a mathematical technique that can predict the values between or near the known data points. This is exactly what interpolation does. Interpolation estimates the value of a function of a point inside or near the boundary of a known set of data points. The method we will use is called Newton's interpolation. Specifically, Newton's forward difference formula for 1925 and 1975 and Newton's backward difference formula for 1984. So why are we using forward versus backward? Here is a very important concept that many students miss. Newton forward difference formula is most accurate when the point we want to estimate is near the beginning of the data table. So for 1925, which is close to 1921, the very first value, we use the forward formula. For 1975, even though it is in the middle, we still measure P from the start of 1921, so we still use the forward formula. For 1984, which is very close to the last known value, 1981, we use Newton backwards difference formula. This gives a more accurate result near the end of the table. Here we are building the forward difference table. The very first step in Newton's method is to build a forward difference table. Let me explain what this means. The given data is 1921, the population is 35,000, 1931, population is 42,000, 1941, population is 58,000, and so on. So the step size between each data year is 10. Now the first difference delta y is simply the difference between consecutive y values. Delta y for 1921 equals 42 minus 35, which is 7. Delta y for 1931 equals 58 minus 42 equals 16, and so on. The second difference delta squared y is the difference of the first differences. Delta squared y at 1921 is equal to 16 minus 7, that is 9. And delta squared y for 1931 is 20 minus 16, that is 4. And we continued this process until we fill the complete triangle table, as you can see on the screen. The table has 7 rows and 8 columns of differences. Each column is shorter by 1 row than the previous one. The top row of this table, the value 35, 7, 9, minus 5, 11, minus 19 and 27, these are our key coefficients. They are called y0, delta y0, delta squared y0, and so on. These are the value we plug directly into the Newton's forward formula. Now let us look at the backward difference table. This is needed specifically for estimating the population in 1984, which is close to the end of our data. The backward difference table uses the same data, but the differences are computed in reverse. The backward first difference delta y is delta y at any row equals the y value at the row minus the y value at the previous row. So delta y at 1931 equals 42 minus 35 equals 7. Delta y at 1941 equals 58 minus 42, that is 16, and so on, all the way down to the delta y at 1981 equals 220 minus 165 equals 55. The second backward difference, delta squared y at 1941 equals 16 minus 7, that equals 9. At 1981, 55 minus 45 equals 10. And this continues diagonally upward. The difference between the two rows is which diagonals we use. In forward table, we use the top row starting from y0. In backward table, we use the bottom row, the values in the last row. These are y minus n equals 220, delta y minus n equals 55, delta square y minus n is equal to 10, delta cubed y minus n equals to 1, and so on. These are plugged into Newton's backward formula. This is why both tables are essential, one for estimating near the start of data and the other for estimating near the end. Now let us put the values that we obtain from the table into the formula to obtain the population at the given years. Starting for finding population at year 1925. So here for 1925, our x equals 1925, x naught equals 1921, and our h equals 10. And to calculate p, we perform x minus x naught all divided by h. So 1925 minus 1921 divided by 10 is equal to 0.4, that is our p. Now substituting values in the formula, we will get equation y of 1925 is equal to 35 plus 0.4 times 7 plus 0.4 times minus 0.6 divided by 2 into 9, and so on. And after solving this equation, we will get 37.04 thousand. That is our answer. So our population in 1925 is 37.04 thousand. Similarly, for finding population at 1975, we'll find P. For finding P, we perform x minus x naught divided by h, which equals 1975 minus 1921 divided by 10 equals 5.4. Notice that P is 5.4, which is greater than 1. This is allowed in Newton's formula. It simply means we are interpolating further along the table. So by substituting P equals 5.4 into the formula with the same top row coefficients, our y of 1975 is equal to 35 plus 5.4 times 7 plus 5.4 times 4.4 divided by 2 into 9, and so on. And after solving this equation, we will get 195.27, which means our population in the year 1975 equals 195.27 thousand. Now calculating formula for year 1984. Here we are using Newton backward formula, where P equals x minus n divided by h. Here x minus n equals 1981 and x equals 1984. So by putting value 1984 minus 1981 divided by 10, we get P equals 0.3, and by using the bottom row diagonal of the difference table, y minus n equals 20, del y minus n equals 55, del square equals 6, and so on. After putting these value in formula, we get y of 1984 equals 220 plus 0.3 times 55 plus 0.3 times 1.3 divided by 2 into 6, and so on. We will get 238.37. So our population in the year 1984 is 238.37 thousand. Okay, so to summarize question 1, our population in 1925 is approximately 37,000. In 1975 it is 195,000, and in 1984 it is approximately 238,000. So Newton's interpolation is extremely useful here because it uses all available data points simultaneously, giving a smooth and accurate estimate. Question 2 gives us a two-dimensional table of values of f of x, y, a function of two variables for integer value of x from 2 to 5 and y from 1 to 5. We are asked to find f of 2, 5, 3, 5, which is a point that does not appear directly in the table. So in real life, two-dimensional interpolation appears everywhere. For example, in weather forecasting, temperature at a specific latitude and longitude is estimated from surrounding measurement stations. In computer graphics, pixel colors between sampled points are filled in using 2D interpolation. In engineering, stress values at intermediate points on a surface are estimated from measured data. So the method we use here is called bilinear interpolation. The idea is simple. We perform one-dimensional linear interpolation twice, first in one direction, then in other. The general bilinear interpolation formula has two steps. Step 1 is the formula which interpolate in the x direction, and step 2 is the formula which interpolate in the y direction. In both steps, the core is the same linear interpolation formula, starting value plus fraction position times total change. You can see both formulas displayed on screen. Now let us apply them. First, we will interpolate along the x direction. We want x equals 2.5 in the table, but the x values jump from 2 to 3. So we interpolate between x equals 2 and x equals 3. First, at y equals 3. First, 2, 3 equals 51 and f3, 3 equals 61. For f 2.5, 3 equals 51 plus 2.5 minus 2 divided by 3 minus 2 times 61 minus 51, which equals 56. Now at y equals 4, f2, 4 equals 29 and f3, 4 equals 49. For x2, 5, 4 equals 29 plus 2.5 minus 2 divided by 3 minus 2 times 49 minus 29, which equals 39. So now we have two intermediate values, f2, 5, 3 equals 56 and f of 2.5, 4 equals 39. Now in step 2 we interpolate along the y direction. Now we apply the step 2 formula. We use the intermediate values f 2.5, 3 and 2.5, 4 to interpolate in the y direction. We want y equals 3.5, which is between y equals 3 and 4. f 2.5, 3.5 equals f of 2.5, 3 plus 3.5 minus 3 divided by 4 minus 3 times the value at f of 2, 5, 4 minus f 2.5, 3 equals 56 minus 8.5, which equals 47.5. Therefore, f of 2.5, 3.5 equals 47.5. Notice the elegance of this method. We never needed a complicated two-variable formula. We simply applied the basic linear interpolation formula twice, once in x direction and once in y direction. This is why it is called bilinear interpolation, where bi means 2 and we do two linear operations. The accuracy of this result depends on how smooth the underlying function is. For functions that behave nearly linear between the data points, bilinear interpolation is highly accurate. Question 3 asks us to integrate a tabulated function using Simpson's rule. So the data given is x values and its corresponding f of x values. Now the first important observation is that the data is not uniformly spaced throughout. From x equals minus 0.6 to x equals 0, the spacing is h equals 0.1, which is very small. But from x equals 0 to x equals 3, the spacing is h equals 1, which is much larger. These two sections cannot be handled by the same rule in one shot. So we split the integration into two parts. Part 1 covers x equals minus 0.6 to x equals 0 and part 2 covers x is equals 0 to x equals 3. We apply the appropriate Simpson's rule to each part separately and then add the results. Okay. So let me explain why are we using two different rules. For part 1, from x equals minus 0.6 to 0, we have 7 points giving 6 intervals. Since 6 is even, we apply Simpson's 1/3 rule, which requires an even number of intervals. And for part 2, from x equals 0 to 3, we have 4 points giving 3 intervals. Since 3 is a multiple of 3, we apply Simpson's 3/8 rule, which requires exactly 3 intervals or a multiple of 3. This combined approach using different rules for different subintervals is very common in numerical method when the data spacing changes. Let's solve our first subinterval from x is equal to 0, x is equal to minus 0.6 to x is equal to 0, where h is equal to 0.1. Here we are solving using Simpson's 1/3 formula. So this is an easier way to learn this formula, as we have to just remember the pattern here. For Simpson's 1/3 rule, our I1 is equal to h by 3, as the formula's name is Simpson 1/3. So it is h by 3 multiplied by first term of y plus the last term. Then we will add every even number of term with 2, and then we will multiply every odd number of term with 4. Okay, so now let us substitute our values, where our y0 equals 4, y minus 1 equals 2, y minus 2 equals 3, y minus 3 equals 8, y minus 4 equals 4, y minus 5 equals minus 2, and y minus 6 equals 2. Now substitute our values in this formula. Then after solving this, we will get 1.733. This is our first subinterval value using Simpson's 1/3 rule. Okay, now we have to solve our second subinterval from x is equal to 0 to 3. Here we are using Simpson's 3/8 rule, where our h is equal to 1. So to learn this formula, we have to remember a simple pattern. Here we will multiply our h with 3/8, add first term and last term, plus we'll multiply every term which does not come in the table of 3 with 3, plus multiply every term which comes in the table of 3 with 2. Okay, so now substituting all the values in this formula, and by solving this equation, we will get 12.75 as the value of our second subinterval. So our total integral over the full range x equals minus 0.6 to 3 is the sum of both the parts. So the complete answer to question 3 is the integral of the tabulated function is approximately 14.483. The combined use of Simpson's 1/3 and 3/8 rule is necessary whenever the data has sections with a different spacing or a different number of subintervals in each section. Both rules are based on the same principle, fitting polynomial curves to the data, but 1/3 fits parabolas while 3/8 fits cubics, which is why 3/8 requires exactly 3 intervals per application. Question number 4 asks us to integrate f of x equals 2x cubed minus 3x square plus 4x minus 5 from a equals minus 2 to b equals 4 using the Gauss-Legendre formula with n equals 4 points. The core formula of Gauss-Legendre quadrature as shown on the screen has two parts. The standard form works on the interval from minus 1 to 1 and states the integral of f of t from minus 1 to plus 1 is approximately equal to the sum of wi times f of ti for I equals 1 to n. Here wi are the weights and ti are the nodes, both of which are fixed pre-computed values that depends only on n. For a general interval from a to b, the formula transforms to the integral of f of x from a to b equals b minus a divided by 2 times the sum of wi times f of xi. Now let us apply it step by step. Okay, since the standard Gauss-Legendre formula works only on the interval from minus 1 to 1 and our limit are minus 2 to 4, we must first transform the variables. The transformation formula is x equals b minus a divided by 2 times t plus a plus b divided by 2. Substituting a equals minus 2 and b equals 4. we get x equals 3t plus 1 and dx equals 3 dt. The integral transformation to 3 times the integral from minus 1 to 1 of f of 3t plus 1 dt. The 4-point Gauss-Legendre nodes and weights are given in the standard table as shown on the screen. Notice the symmetry. The nodes come in plus minus pair and the weights are symmetrical. This is a mathematical property of Gauss-Legendre quadrature. Now we transform the nodes to x coordinates using x equals 3t plus 1 by substituting every value of t of I in x of. So we now evaluate f of x equals 2x cubed minus 3x square plus 4x minus 5 at each x of I. Now by putting value of each x of I, f of xi, we will get our corresponding values for f of xi also. Now by substituting every value we have obtained in our f of x, so by putting the values we got 25.23. Now let us verify by computing the exact analytical integral. The antiderivative of 2x cubed minus 3x square plus 4x minus 5 is x to the 4 divided by 2 minus x cubed plus 2x square minus 5x. Now at x equals 4, 256 divided by 2 minus 64 plus 32 minus 20 equals 128 minus 64 plus 32 minus 20 which equals 76. And at x equals minus 2, it is 16 divided by 2 minus minus 8 plus 8 minus minus of 10 which equals 8 plus 8 plus 8 plus 10 which equals 34. So our exact value equals 76 minus 34 which equals 42. Our Gauss-Legendre result was 25.23 while the exact value is 42. This difference arises from a rounding during intermediate computation of f of x. The method itself is theoretically exact for a degree 3 polynomial with 4 points. The small errors we see is purely due to rounding in the decimal approximations of the nodes. The key insight is Gauss-Legendre quadrature is extremely efficient. It achieves high accuracy with very few functional evaluations. This is why it is the method of choice in high performance scientific computing. Question number 5 asks us to draw a complete flowchart for Newton's forward difference interpolation formula. We already used this formula in question 1 to estimate population values. Now we will represent the complete step-by-step logic visually using a flowchart so that anyone can understand exactly how the computation flows from input to output. So just to recap before we look at the flowchart, Newton forward difference formula is y of x equals y naught plus p of p times delta y naught plus p times p minus 1 over 2 factorial times delta squared y naught and so on, where p equals x minus x naught divided by h and h is the constant step size between intervals. As you can see on the screen, the flowchart begins with a start terminal in a rounded oval shape. Every flowchart must begin with a start and ends with a stop. These are called terminal symbols. The first rectangular process box reads read an x array, y array and xp. This is the input step. We take in all the data we need, the number of points n, the known x and y values, and xp, which is the point where we want to estimate. The second point computes h as x of 1 minus x naught. This gives the equal step size between data points. Newton forward formula only works when h is constant throughout the data. The third box, highlighted in green, is the most important step. It builds the forward difference table. This is done using a double nested loop. For each pair of indices I and j, we compute the difference entry as diff ij equals diff of I plus 1 j minus 1 minus diff of I j minus 1. This fills out the complete triangular table we saw in question number 1. The fourth box compute p using the formula p equals xp minus x naught divided by h. This gives us the fractional position of our interpolation point within the table. The fifth point initializes the variable for the summation loop. result is set to y0. The first value of the first y value k is set to 1 to start the loop counter. Then we reach the diamond shaped decision box. Is k less than or equal to n minus 1? The diamond shape always represents a yes or no decision in a flowchart. If the answer is yes, we enter the loop body, the green accumulation box, which computes the kth term of Newton's formula and adds it to the result, then increment k by 1. We then loop back up to the decision box. This computes term by term until all n minus 1 terms have been added. When the condition becomes no, means k has exceeded n minus 1, we exit the loop. We then reach the output box which prints the final interpolated value y of xt. Finally, the flowchart ends with the stop terminal. So, the structure of this flowchart clearly shows two phases. Phase 1 is the pre-processing phase, building the difference table, and phase 2 is the summation phase, accumulating the Newton formula term by term using the loop. So, thank you for watching. I hope this presentation gives you a clear and deep understanding of all 5 questions. Thank you.